Hello everyone, this is Professor Pawan, and in this video we are going to solve an SFD and BMD problem based on a simply supported beam loaded as shown in figure. Now here we have a simply supported beam which is loaded with help of a point load, a UDL and a couple like this. Now, first thing we need to do before drawing the SFD and BMD is finding the support reactions. That is, we have two supports here, one at A and one at B, and hence we'll be having two support reactions in upward directions, that is denoted by RA upwards and RB acting upwards. So to find out the magnitude of support reactions, I need to consider the force equilibrium equation first. And the force equilibrium equation in this particular case says total upward force is equal to total downward force. That is, total upward force is equal to total downward force. Now the total upward force acting here is due to RA and RB, that is RA plus RB, which is total upward force, is equal to, now we have two downward acting forces here. One is this point load and another is this UDL, and UDL is load intensity, which we need to convert it into the equivalent load, which we do it by multiplying this load intensity into the length over which UDL is acting. So let me first write down the downward acting load, which is 40 kilonewton, plus this UDL I'll convert into load intensity by multiplying 10 into the length on which it is acting, 10 into 4. So here we get that RA plus RB is equal to 80 kilonewton. Let us consider this as equation number 1. Next, we need to consider the moment equilibrium equation now. That is, I'll consider summation of moments about A is equal to 0. That is, I need to consider the summation of all the moments about point A now is 0. That is, I need to consider all the moments due to the forces and couples which are acting towards the right side of point A, and I need to make it equal to 0 because we know that at supports here the moment is 0. So what I'll do is first I'll consider the moment due to this point load, and the moment due to this point load about A is trying to move it in clockwise direction, or it's trying to create a bending moment in clockwise direction, which is negative. So I'll have to take minus 40 into the distance from A is 2. This is negative because, as I said, it creates a clockwise bending moment. Next, I need to consider this UDL. This UDL also is acting in downward direction compared to A, and this also will create the clockwise moment, and hence that also is negative. Minus of, at first I need to convert this into load, which I do it by multiplying this intensity into the length 4. Next, I need to multiply it by the distance from A. Now we know that the equivalent load of the UDL lies exactly at the midpoint of UDL, that is 2 meters here from here. So this distance from this point, from point A, is this 2 plus this 2, that is 4 meters. So here I take it. Next, I have this clockwise bending moment, which is given directly, that is minus 30. Next, I need to consider the moment due to RB. The RB is creating anti-clockwise moment now, and hence that will be positive. So I'll write plus RB into the distance now is, the RB's distance from point A is 2 plus 4 plus 2, that is 8 is equal to 0. And if I calculate this, I'll get the value of RB as 33.75 kilonewton, and if I substitute the value of this RB in equation 1, I will get the value of RA as well, which is equal to 46.25 kilonewton. RA is equal to 46.25 kilonewton. So this is how we have found out the support reactions now. That is RA is equal to 46.25 kilonewton and RB is equal to 33.75 kilonewton. Next thing to do is to start drawing the SF for this diagram. That is, start finding the shear forces at salient points and ultimately drawing the shear force diagram. So that's what we're going to do now. So we start finding the shear forces at salient points in this figure, starting from point B and ending at point A. That is from the right side end to left side end. Now let's come to right side end. First I know that SF at B is equal to, now SF at B is due to RB and RB value is 33.75, and since it's at the right side and it is acting upwards, so that shear force is negative, and hence I'll take this as minus 33.75 kilonewton. SF at B is minus 33.75 kilonewton, and this remains same till point D, same till point D. Now what will happen at point D? At point D we have a UDL starting from point D to point C, and hence the shear force here will increase as inclined line from D to C. So till D the shear force will remain same, that is minus 33.75. Hence we need to find out the shear force at C now, and that we do first by neglecting this point load and second time by considering this point load, that is shear force at C. First neglecting point load, that is first what we do, we neglect this 40 kilonewton. So what do we get? RB, and this we need to consider, that is minus 33.75, and this will be plus because this is on the right side and it's acting downwards, so plus, we need to convert this UDL into the load, that is 10, which is its magnitude, into 4, that is the distance over which it is acting, So here what I get the value of it as 6.25 kilonewton. Okay. Next, I need to calculate the shear force at C again. Now I'll consider this point load. Considering point load. Now I'll consider this point load along with what I have calculated. That is what I calculated. I have calculated it to be 6.25 kilonewton till now. Now I'll consider this point load as which is again on the right side and acting downwards, so it is positive. So 6.25 plus 40 makes it 46.25 kilonewton. It's 45.25 kilonewton, and again we know that there's no other force now acting from C to A, and hence it will remain same, that is 46.25 till C to A. So now let's start drawing the SFD for this first. Now I have projected these lines here. So that I can draw SFD and BMD below that. So first let me draw the datum line, that is the zero line. Datum line is zero line. So first I know that shear force at B is minus 33.75. So it is, and you all know that the positive values are plotted above the datum line and negative values are plotted below the datum line. So first at B it is minus 33.75. I'll take it minus 33.75 like this, and it remains minus 33.75 till point D. Okay. It remains constant. So this is minus 33.75 kilonewton. Okay. Next, I have found out its value at C first, neglecting this 40 kilonewton. And by neglecting that 40 kilonewton, I got the shear force at C as 6.25 kilonewton, which varies from D to C in uniform manner. D to C in uniform manner, that is, I have to consider this like this. Uniform linear manner, and now I got this as 6.25 kilonewton. Next, I have found out the shear force at C by considering this 40 kilonewton load. Then what I get this value as 46.25 kilonewton, and this will remain 46.25 kilonewton till point A. So basically it remains constant like this here. So I have drawn it like this, and this thing is positive, this value is negative here. I'll shade the diagram like this, and this also is 46.25 kilonewton. Yeah. So this is the shear force diagram for this. This is the shear force diagram for this. Now, next thing I need to do is I noticed that at one point here the shear force becomes 0, and I want the location of this point where shear force is 0, because at this particular point the bending moment will be maximum. If I don't find its location, I will not be able to find out the maximum bending location, which I need later in bending moment diagram. So first what we'll do is we'll find out the location of this point where shear force is 0. What we'll do is we'll assume that, let this be section X at a distance of, let it be at a distance of X from right hand side. It is somewhere here. Okay, it is somewhere here. Now we know that shear force at XX is 0. We know that shear force at XX is 0. That is, I'll write it down. SF, shear force at XX is equal to 0. Now what I'll do is I'll consider the shear force at this section XX due to all the forces that are acting towards right side of this. So first I got is RB, and RB I know it is minus, and I know the value of RB as well. How much is RB? RB is minus 33.75 kilonewton. And next I need to consider this UDL as well. So I know that this UDL is positive since it's acting at the right side and it's acting downwards. And first I'll write this 10 into, I need to multiply this 10 not by this whole 4 meter distance but only this distance. And how much is this distance? Is it not this X minus this 2 meters? So I'll write 10 into X minus 2, and that we equate it to 0. And once we do this, once we solve this equation for X, I'll get the value of X as 5.375 meter. I'll get the value of X as 5.375 meter. Now this will be helpful for us while we draw the bending moment diagram, because we need to find out the bending moment at XX as well, which will be the maximum bending moment. Now, so we'll start drawing the bending moment diagram now. That is by finding bending moments at all the salient points. Bending moments at all the salient points. So let's start from point B and we'll move on to point A, that is from right side end to left side end. So bending moment at B is equal to, it's definitely 0. Bending moment at B is 0 because it's the support and we do not have any load which can create the moment about it here. So bending moment at the support here is 0. Next, if we come at point E, that is bending moment at next point E, I have this direct couple as well as the bending moment due to this RB. But what I do at this point, I'll have to find out bending moment twice, once by neglecting this couple and second times by considering this couple. So first what I'll do, I'll find out bending moment at E by neglecting couple. So by neglecting couple, what I get bending moment here to be RB into 1, and RB, since it's creating anti-clockwise moment, it is positive, and I know the value of RB. So how much is it? RB is it is 33.75 into the distance from point E, it is 1 meter, so it becomes 33.75 kilonewton. Next we'll find out the bending moment at E with couple, that is I'll include this couple which is negative because it's acting in clockwise direction now. So I'll write bending moment at E with couple will be equal to the previous couple value, neglecting the previous value was 33.75 minus, I'll consider this couple, so it becomes 3.75 kilonewton meter, and I have subtracted it because it's negative since it's acting in clockwise direction. Next I'll have to find out the bending moment at point D. So first I'll consider this force RB, which is 33.75, and RB is causing anti-clockwise moment and hence it will be positive. So I'll write RB, which is 33.75 into the distance from point D. Distance from point D to RB is 2 meter, and I'll have to subtract this couple now, minus 30. That is, basically I'm calculating moment at this point by considering all the moments towards the right side of this D. Okay. So what I get, bending moment at D is equal to 37.50 kilonewton meter. 37.50 kilonewton meter is what I get. Okay. Next, I'll find out bending moment at C now. Bending moment at C will be equal to, I'll have to consider again this RB and this couple and this UDL now, which comes into picture. So first I consider RB value is 33.75. It is anti-clockwise and hence it's positive, and the distance from RB to C is 6. So minus 33.75 into 6 minus this couple, which is 30, and again this I need to consider now, which also is minus because it also is creating clockwise couple like this. So what I'll write here, minus, first I'll convert this into the load, that is minus this 10 into the length, which is 4, 10 into 4, and I know that this load acts exactly in the middle of UDL, and middle of UDL to C distance, how much is it? 2 meters. So minus 10 into 4 into 2, this equal to, how much is it? We will get it as 91 kilonewton meter. 91 kilonewton meter. And ultimately, if I found bending moment at A, it will be equal to, that is at support it will be equal to 0. So bending moment at support, it will be equal to 0. Also, we need to find out bending moment at one salient point, which is this bending moment at XX, that is maximum bending moment, because at XX I know that shear force is 0, and the point or section where shear force is 0, the bending moment will be maximum. And I know the distance X now. How much is the distance X? Distance X is we found it out. The distance x is 5.375 meter. X is equal to 5.375 meter. So next what I'll do is I'll find out bending moment at xx, that is maximum bending moment. Maximum bending moment at xx is equal to, I'll again consider bending moment due to all the forces that are acting towards the right side of xx. So how much is this? First I'll have to consider RB. So RB is positive 33.75 into this distance, which is x. X is 5.375. Yes, this is done now. Minus this clockwise moment, that is minus 30. And next I'll have to consider this 10 kilonewton per meter UDL, but I'll have to consider this not till this point but only till the section XX, like this. So I need to know what is this distance. This distance, is it not x minus 2? That is 5.375 minus 2, that is 3.375. So I'll write here minus 10 into this length is 5.375 minus 2, that is 3.375, into, I need to multiply it by the distance between the midpoint of this and this xx. So if this is 3.375, the midpoint will be 3.375 by 2 into 3.375 by 2. If we calculate this, we get the value as 94.453 kilonewton meter. So now we have found out the bending moments at all the salient points. So it's time for us to draw the bending moment diagram now. Okay. I'll again project these lines downwards so that I can draw the bending moment diagram correctly. So what I'll do first, I'll just draw a datum line like this, that is 0 line. At B the bending moment is 0. At E we have found out the bending moment twice. At E we have found out the bending moment twice, once by neglecting the couple and second times by considering the couple. So without couple we got the value of that as 33.75 kilonewton meter, and the variation from here to here will be linear variation. This value is 33.75 kilonewton meter. Okay. Next, at E we found out the bending moment again without considering, with considering the couple, and with couple we got the value as it becomes lower actually, 3.75 kilonewton meter. Let this be the point, 3.75 kilonewton meter. Okay. Next, we have found out the bending moment at point D, and bending moment at point D is how much it is? 37.50 kilonewton meter. So it comes somewhere here, and again the variation from here to here will be linear variation. .50 kilonewton meter. Next, we have found out the bending moment at section XX now. So how much is that value? That value is 94.453 kilonewton meter, and the variation here will be parabolic since we have the UDL here. For UDL the bending moment variation will be parabolic. So from here to here, I'll draw a parabolic curve like this, and this value I know how much is it. This is 94.453 kilonewton meter. Next, we have found out bending moment at C. Bending moment at C is 91 kilonewton meter, and again we have a parabolic curve here because this again is UDL in this portion. So here I'll write 91 kilonewton meter. And next, we know that bending moment at A is 0, and the variation from A to C will be linear variation because we do not have any UDL or UVL here. So it will be linear variation like this. So this is the bending moment diagram for this particular problem. Hope you all understood this problem. If you like this video, do hit the like, share and subscribe button. And if you have any doubts, please write them down in the comment section. I'll definitely answer them. Thank you.